마지막 수업이네. 쳐줘야 되는 거 아니야? 5인치야. 알겠어, 마킹. Not CC double bond, CO double bond. 이러지 말자. If you don't have any other heteroatoms, the regularity is around 1 ppm. TMS 0 as reference. One heteroatom plus 2, so about the 3 ppm. Two heteroatom. About 5 or 6. 3 heteroatom. About 7. Above 10 is exceptionally aldehyde of the carboxyl acid. They don't go that much. 설마 아세톤의 구조를 모르는 건 아니겠지? 아세톤, alpha position, about 2. Aromatic ring is about approximately 7. 또 고개를 갸우뚱하고 그래. 불안하게. Material position. Alpha position하고 가르보네요. Benzylate position 2 ppm. Last time we had the 5 ppm because it had a double 3 ppm effect, 2 ppm effect. Added together, that was a 5 ppm last time. Okay? 준다. 1분 준다. ppm should be this big. Chloro is attached to here, so this big is coupling with this proton. So this proton is single, so you will get the W. Same molecule. Okay, so in that case, this one is a coupling with this, 6 there, that's why you will get the 7 pick, 7. Okay? This is 6, 5, 8. One, two, three, symmetric, same. 1, 2, 3. Same molecule, hydrogen signal, proton signal. 내가 답을 잘 맞춰보네. 1, 2, same, symmetric. 2 sets. 야, 이 정도로 준비가 안 됐으면 어떻게 수업을 하니? 이거 한 번 더 할까? 100% 나올 때까지 계속 반복하고 수업 들어갈까? 내가 하나씩 이렇게 다 떠먹여 줄 수는 없잖아. 이 정도 준비를 해와야 NMR을 듣든지 말든지 할 거 아니야. 자, 시간 많이 안 남았다. 다시 하는 건 오늘 마지막이고. Okay, following the last class, we continue the practice. Starting with this. Okay, this is my tip. 누가 해볼래? Degree of unsaturation. 0. 6 plus 2, 8 minus 6 minus 2, 0. And peak-wise, you have a 6 proton, 1, 2. That means this is a 2 proton, this is 3 proton. Sorry, 2 proton, 4 proton. And it looks like a symmetric. Three point something, this may be attached to heteroid. This may be just nothing. coupling, triplet, something more. 자, 누가 해볼래? 주의가 먼저 듭니다. 좀 크게 그려라. 뒤에서는 안 보이지. 아, 다시. 반항하는 거지. 너무 리얼리스틱하게 이것도 프로ton 너무 작게 그리지 말고. Okay, Jung proposed that structure. Let's check whether that makes sense or not. Here, this proton, 4 proton, and 2 here, symmetrical, and then they are interacting with this 2 proton here, triplet, makes sense. And this one, carbon, carbon, so that's why this one is 1 point something, a little higher, maybe a little remote effect from here, but still, that's not 3. Okay, this one is connected to carbon, and this one has 1, 2, 3, 4 proton around. So then you expect 5 peaks. Looks like a reasonable model. Now, proton number 6, carbon number 3, bromine 2, matching. So you can draw this kind of model, and then you can check whether your structure is correct or not. Okay? Good. How about this? 아, 엄청 심플하네. Now, degree of unsaturation. Degree of unsaturation. 경민아, degree of unsaturation? 4. If it's a carbon number is small, if you see 4, most likely it has a benzene ring. 3 double bond and ring, that count to 4. Okay? Then 1 benzene ring, it covers the 4. So then, benzene ring, and then extra 1 carbon, and looks like a quite simple structure here. Okay, double over double. Then also meta para, you have one option, simplest one, and then other combinations. 이거 해볼래? Okay, Gilman suggested this structure, and let's check. So this peak, now let's count the carbon number, the proton number. 1.511 is a double of them 3, 2, 2, right? 3, 2, 2 means 3, 2, 2. 3, maybe this one. Is this a 3? No. Also, para double over double, 4 proton. Here, how many proton? 5. And it may not give that simple structure. Model is wrong. Okay, who is going to fix it? Molecular formulas are correct, but connectivity is something strange. It doesn't match. 누가 고쳐볼래? 마지막 수업인데 이해하네 한번 해볼래? 다음에 할래? 누가 한번 해볼래? 이해하네 해볼래? 고쳐. 각도 바로 잡아줘. 똑같은 마음 편하네. 아까 막 찌그러져 있으니까 막 뒤틀린 것처럼 막. You should be 120 degree. 그래나. Okay, carbon number 7, proton number 7. Seems like the atom number is the same. Atom number is correct. Now let's look at here. 3 proton may be matching with this benzene position about 2 ppm something. Okay, matching. Now pattern of this. If you look at this, now this is meta position. Then if there's any proton here, this proton may be doublet. This proton may be singlet. This proton may be doublet. This proton may be double of double. Is that matching with it? So that's much simpler, right? Then you expect 4 different peaks there, but here this is not each peak. This is 2 peak, 2 peak, 2 peak, 2 peak. If you want to make it symmetric, 그대로 할래. 말하지 말고 바꿔. That's a para position. Okay. If this is a para position, if this is a para position, this is a symmetric, and then these two same, 2 peaks each you will see, and this one doublet, this one also doublet. So if you see double of double, oh, this is 점수 줄라도 만들었구나. 가장 심플한 구조 하나밖에 없어. Also is also complicated. Meta is also complicated. Just a single is also complicated. 파라가 제일 심플해. 더블 오브 더블을 세븐 능력에 줬으면 아, 벤젠링의 파라 포지션이구나. 이건 점수 주려고 만든 문제구나 하고 생각할 수 있어야지. Okay, move on. How about this? Now, proton and carbon. And degree of saturation. Four or 5? 4. Hydrogen is the same as hydrogen. So 8 by 2, 16 plus 2, 18. 18 minus 10, 8 must divide by 2, 4. So 1 benzene. 1 benzene, and then you try to match with this. And if you look at this pattern, this is symbolic pattern to something, right? 3 proton, 3 proton here, 2 proton here, and triplet and quartet. What is this thing? What is that? 뭐라고? 어? 크게 얘기해. 3 proton, 2 proton, triplet, quartet. That's an ethyl. Ethyl. Okay? Ethyl is there. 6 carbon and ethyl. Yeah, 거의 다 나왔네. And this pattern again. 야, 너무 쉽네. 뭐 그냥 쭉 하나 더 떴네. 맞는지 확인해 볼까? 하나씩 매칭해봐. Using that structure and then assign those peaks each other. Which peak is which?
일단 뒤에 두 개가 있지.
Okay, which one is which? Here, this one is matching to which one?
이거
Because
왜냐면 브롬이랑 더
it has a near to bromine, so there is some electron withdrawing effect. That's why this may go to further a little downfield. Okay, weak effect, but still there is some effect by this. So this is para position, double over double, and then this one, the position is a benzylic position, approximately 2 point something. And this is 1 point something, next to another carbon. So this is proton matching, and then carbon.
하고 아 밑에 게 카본.
Yes, it is a carbon element, carbon 13 element. 수고했다. 들어가, 내가 할게. Proton NMR is usually from 0 to 10 ppm range. There are other NMRs, fluorine NMR, phosphorus NMR, but in your level, just the proton NMR and carbon NMR. Carbon is about 0 to 200 range. And then similar, about 10 times bigger than this, you can think. So this peak is matching to this, around 10. This position is a little higher around here. So in carbon NMR, if you have this is benzylic position, right? Benzylic position, carbonyl alpha position is approximately 30-40. If you have a heteroatom, it's going up around 40-50, a little higher. So similar pattern you can expect. Here, carbon 2 peaks. And this is aromatic ring around the 120 to 140 range. And bigger one, we are matching this one and this one, 2 each. And small one, maybe this one and this one. Can you tell which one is which? So this 140 something one is this one or this one? Again, bromine side is electron withdrawing, similar effect, it goes to the little further downfield. So in carbon, if you look at around this range, this is all aromatic rings, 120, 140. If you see anything around 200, what is the peak? All active peaks coming around here. Aromatic rings around 120. If you see anything around 200, what is the peak? Carbonyl. CO, carbonyl, carbon. Okay. Okay, next. This. Igor saturation. It's a 4. Again, one benzene ring. And pattern is not so simple. And how many proton there? How many proton there? This range, this area. This is a relative ratio, right? Altogether 3, 4.5 is 9, then you should double. Then how many proton here? 5. If it's a 5 proton here, then only one substitution. 5 is aromatic ring. Then left over 2 carbon and bromine you need to assign here. 2 proton each, and then seems like it's a triplet and triplet. 누가 해볼래? 유빈이 했나 아까? 안 했나? 안 해요. 맞는지 한번 매칭해봐. 45 산대로 100원 매칭 부딪히기. Okay, so this pig is near to bromine, so this is a little further down. This one is at the angelic position. This one in the sign. 대충 넘겨보면 okay, five pigs here, showing up here. Okay. Each one has two nearby, so triplet. If you see one of them quartet, you should suspect that's an active group. If it's a triplet, then CH2 is a connected. Okay? How about this? Degree of unsaturation? Is that false? One. Oh, degree of unsaturation 1. Either ring or one double bond. Okay? And if you look at those structure, everything is around here. And how to use the oxygen is the issue. If the oxygen directly attached to the carbon, you should see 3 point something, but you don't see that. If oxygen is directly attached, then you should see something above 3, but you don't have that. And that implies something. And there is some pattern. Here, triplet, not quartet, so it's not fully ethyl. But anyway, it has 5 carbon. That structure. And there is singlet 2, singlet P, 2 point something singlet. How many of them? 3 proton as a singlet. 지금 또 할까요? 이번 이쁘게 그릴 수 있어? 해봐. 이번에 CH 안 쓰고 이제 한 큰 다 그렸네. So with this 매칭 한번 해볼래? 어디 가는 거지? 안 보인다 야. 말로 해봐. 이건 어느 픽이고 이 픽은요 이거고요. 찝어.
트랭크 시프트 0.9가 여기 밑에 있는 거고
커플링 패턴은 맞아?
여기 H 두 개 있으니까 수신을 만들어서
오케이. 이게 이 픽이고 그리고
그리고 1.64에 이제
전부사 있는 거고
그 6개 피크가 나오는 거에 이제 하이드로젠 같은 거니까 여기 사이에 있는 얘
걔가 두 개일 것 같다. 그리고
그다음에 이제 여기는 HCG 두 개 있으니까 이제 적분량 비교해가지고 여기가 2.17, 여기가 2.4.
저거는 싱글렛으로 나올 거고 3개 있는 거고 여기는 2개 있고 여기는 좋네. 모델이 그렇다. 여기는 이 픽은 원래는 여기 3개 여기 2개니까 퀄텟 트리플렛 해서 얘는 여기 2개 있으니까 트리플렛으로 나오는 거 맞고 얘는 여기 2개 있으니까 트리플렛으로 나오는 거 맞고 얘는 아무것도 없으니까 싱글렛 나오는 게 맞고 포지션을 봐서 2 point something. 얘는 여기 2개 있으니까 3개 여기 3개 있으니까 4개 원래는 12개가 나와야 되는데 얘랑 얘가 비슷하면 그러면 여기 2개 있었고 여기 3개 있었으니까 합치면 5개 비슷하면 이 12개가 다섯 개가 있는 효과 6개처럼 보인다. 그러나 더 좋은 NMR 가지고 자세히 들여다보면 조합의 픽들이 이렇게 막 갈라져 있어요. 이렇게 조그만하게. 그 닷에 보면 12개가 나와요. 조금 안 좋은 NMR로 찍으면 대충 비슷한 것들이 뭉쳐져서 같은 픽처럼 보인다. 원래는 커플링 컨스턴트가 다 다르기 때문에. 그러나 우연히 비슷했기 때문에 마치 섹스테시처럼 보인다. 오케이? 그래서 모델을 이렇게 맞춰보면 중요 모델이 제일 그럴듯한 문제입니다. 다 됐네. 또 재밌는 문제가 하나 있는데 문제가 안 나왔나 봐. 오케이. 자, 그러면 연습은 이 정도로 한 걸로 하고, 여러분들 봐서 알겠지만 당연히 연습이 많이 필요하겠지. 우리가 시간이 더 많았으면 한 2시간 정도 더 구조 푸는 거 하고 했으면 좋았겠는데 시간 여기까지밖에 안 되니까 각자 13장에 내가 앞쪽에 있는 문제들만 이렇게 풀어보라고 했고 뒤에 있는 문제들은 안 줬어. 뭐 거기서 뽑아온 것들이 대부분이긴 한데 문제들 돌아와서 교과서에 있는 문제들 풀어보면서 연습을 좀 해. 중간고사 이렇게 또 볼 거야 여러분들이. Okay, so before we close the class, let's just summarize the reactions, what we have learned so far during the second part of the semester. So we started with the alkene. Alkene, naming wise, alkene, alkyne, if you have both, then you keep the lowest number. If the number is the same, which is a higher priority, alkene or alkyne? Alkene is a higher priority, okay, when the number is the same. Other than that, in alkene, you have a chance to look at cis and trans. This is a cis, this is a trans, but systematic name-wise, we have another notation, E and G. So E is antibiagan, it's the opposite. G, 주장면, on the same direction. So it seems like this is the cis, but the priority, the rule is different. In this case, they give those a high priority for higher atomic number. So the same rule has been applied to which case? When we give those the order, we use alphabetical order, but one case we have seen this kind of a higher atomic number we gave to assign something. Which one is the case? RS configuration, right? RS configuration and also E and G configuration, we use atomic number. The higher atomic number is a higher priority. Okay, that's why seems like cis is not G. So in this case, this is higher, this is higher. So this is the opposite direction. That's E. Okay, systematic name and the system transit can be different. Now from alkene, if we do hydrogenation or reduction, then you can get the same product. Now by looking at those structure, this one and this one, trans and cis, which one is more stable? Trans may be more stable. How do you know? If you measure those energy difference, cis and trans, if you generate the reduction product, the same product, then this value is the same. Then you can measure those relative energy here and here. So this energy is a thermodynamic energy, and that's why this is delta G, right? So that's why this is more stable, means it's a lower energy, right? So higher energy, that's why it has more energy released. So this difference determines those direction of a reaction, delta G, that is related to the equilibrium constant. And this energy is activation energy that determines the speed of the reaction, not direction. And that speed, which is the faster, trans or cis, which reaction is the faster? Trans is faster. Can you really say so? Activation energy is between this to this, right? So if you compare this one and this one, if they are same, then speed may be similar, right? Not comparing here and here. Right? So if you look at those the transition state, then this notation you use not delta G0, you use delta G double dagger. This is about the activation energy. Okay? So that's the notation difference. Okay, here those stability, more substitute one is more stable than less substitute one. And explanation, there's two kinds, sp2, sp3. The bonding is stronger is one explanation. The other explanation was hyperconjugation. More hyperconjugation can further stabilize. Anyway, result is more substitute one is more stable than less substitute one. That was the property. And then reaction wise, now here if you look at this alkene, electron poor or electron rich? Electron rich because it has an extra pi electron. That means alkene is a nucleophile or electrophile? Huh? What do you say? It should be nucleophile. It has more electron. Then if you add acid, nucleophile can act as base too. Okay? Base attacks proton. So this extra electron can donate to proton. It can capture proton. And then chloride, Cl- can come back and attack behind if it is SN2. Now we have learned SN2, SN1. If that forms carbocation first, protonation happens here, then carbocation forms here. Now we learned SN1. This is not exactly SN1, but seems like by adding acid condition, it can generate the carbocation as an intermediate. If it forms carbocation, primary position versus the tertiary position, which is more preferred? Tertiary, because tertiary carbocation is more stabilized. Okay. Even before we learned SN1, we have learned this kind of reactions in terms of alkene reaction with acid. Okay. Now, because of this selectivity, more substitute position is exchanged. That rule is Markov-Nikodym rule. More substitute position is the having another the substitution. So that rule is Markov-Nikodym rule. Usually that happens. And carbocation has a sp2 structure and it has a planar structure like this. And then if it is SN1 intermediate, then attack of a nucleophile come here or come here, it can generate mixture of RNS. Full racemization is the problem. And reaction. As you have seen, if you add acid, first reaction is protonation happens first. If it forms a carbocation, it may be more SN1 type. Or if it forms cyclic structure, X minus attack behind, then it may be more SN2 type. Okay, depending on the cases, you may see different results. Now, if you add halogen, X2, if it's fully ionized, then that should be X minus. But X2, extra electron of the alkene can donate to this one first and capture the first one. Then this one behave like an X plus. This is an X minus. Okay, so intermediate is bromium, cyclic structure of intermediate forms here, and then X minus attack behind. This is more typical SN2 reaction. It's a SN2 reaction, that's why the reaction product is anti-addition. One is added here, and then the other one coming behind and attack and release. So that's SN2 reaction. So 이거 배울 때는 우리 SN1, SN2를 안 따졌지만 이제 우리 SN2를 배웠으니까 because of that selective attack position, that's why this is the anti-addition, opposite direction. Okay. If it's not, if it's SN1, there's no opposite direction, it's randomly added. Okay. And here, activating of alkene with the halogen, and then if you add the excess amount of water, then it will compete. X minus compete with the water. You may have a chance to get one part bromium, and then the other part, rather than X minus, excess amount of water attack behind and generate hydroxyl compound. Again, in this case, if it forms bromium intermediate and then attack SN2 type. Now there's a competition between X minus and water. 똑같은 말을 계속 하고 있는 거지. Now, adding acid is a little messy for the reaction. To make it a little more selective, you can add metal cation as a Lewis acid. So mercury is the choice. So adding mercury and then water attack behind. And then remove that mercury with a reducing reagent. Then the product is hydroxide is added. Again, mercury is added here first, similar to acid H+, but it's easier to control. And then water attack behind, and then mercury moved to this direction, and then mercury is removed reductively. Then mercury is removed here. Okay, reaction is similar to HX reaction. Acid is added first, and then nucleophile attack behind and open up. And product position wise, this attack position happens more substituted position. That's why this oxymercuration happens following the Markov-Nikov rule. Okay. Similar reaction but opposite selectivity using boron reagent, hydroboration. In this case, B, H2, and H is added together. So here, B coordinated, H coordinated, and then added together, and then that B is removed by oxidative cleavage. So hydroxyl group is added to B position. And this product generates less, so B here in this case, and then H coordinated here. So this position is less substituted position is attacked by B because of the static effect. So in this case, the adding of B and H, it is added together. So first addition here, this is syn addition. B and H was added together. Mercury case, mercury was added first, and then water attacked behind. So it's the entire addition. Hydroboration, pH was added together, it's added one same direction, and then that B is replaced by oxidative cleavage here. So that's why still this is a syn addition. Okay. Hydrogenation. On metallic surface, if you add hydrogen, like this. So this is a typical anti-addition or syn addition? This is syn addition. Okay. So this is added side by side like this. So that can be done by palladium or platinum metal surface and hydrogen gas. Reduction and hydrogenation. Okay. And peroxide, similar to hydrogen peroxide, H2O2, but just to make it organic solvent soluble with the IQ group. So best example here is, anybody remember the reagent name? NBC, similar, M-chloro benzoic acid, MCPBA. Okay, so MCPBA, if you add, then what is your product? One oxygen is added to form epoxide. Okay, it's an addition of one oxygen over here to this. Epoxide is a reactive intermediate, and it can be attacked by another nucleophile and then open can happen. Right? So another reaction. Not only single oxygen addition, two oxygen reaction. Osmium tetroxide, adding two oxygen together. Product is diol. Osmium tetroxide is very expensive and toxic. So we don't want to use excess amount of that to make it recycled. So by adding N-methylene and oxide. This kind of reagent. Then we can recycle, regenerate the osmium tetroxide. Now this reaction is quite interesting reaction. Chloroform, strong base. Chloroform has a 3 chloro, that's why 3 electron with the direct group. And this proton is quite acidic. So strong base can capture that proton. And then CCl3 minus is formed. and then one cell is leaving as a chloride, and that generates in situ this kind of a species. Two, the electron together. This is not radical. What do you call this kind of reagent? Carbene. Carbene reagent is formed. It's a two electron. That's why it can be inserted into double bond, similar to oxygen, and it can form this kind of a cyclopropane structure. It's a very interesting reaction. The problem is it has always carrying two chloro. Sometimes we don't want to have a chloro, just we have to have a CH2. That reagent is developed by Simon-Smith, maybe two persons developed together, and in this case, CH2I2, and then we have seen some metal addition to there. Metal is added here, and then remove this, and then in situ generate the CH2 carbon. And then this reagent can add this position, this structure, and then generate the cyclopropane. Simon-Smith reactions, carbon reaction. And oxirane or the oxide, adding acid condition or base condition, either one. And then this one can attack from behind. Acid activate this one, and then water attack behind, and SN2 reaction. In this case, the water attack this position here, and then bring up entire addition, SN2 reaction. Okay. If it's a stereochemistry other there, then you will see a different product. Not syn addition, this is entire addition, because it's SN2. Inversion happens. Okay, ozonolysis. Double bond by adding ozone in the middle, and then break it up. Then you generate oxygen in both sides. There's two ways of workup. You added metal. Is that oxidative or the reductive? Metal powder. Reductive. Okay. Oxidative is hydrogen peroxide. Permanganate is oxidative. Okay. Metal powder is always reductive because it can donate electrons. So cleavage in the middle, if it's everything is a substitute, you don't see difference. Anyway, you generate this one. Oxidative way, permanganate is a typical strong oxidant. And oxidative way, if you add, if it is fully saturated, the product is the same. But if that has different substituent, then product is different. Oxidative condition can oxidize further. Once this is the breakup here, it generates here aldehyde, right? This generate the formaldehyde. Those aldehyde can be further oxidized and can go to one side becomes acid. This position becomes acid. This one, formaldehyde, can be oxidized one side and the other side too. It can be fully oxidized to CO2. If you wanted to block the reaction in the middle, not fully oxidized, then you have an option: ozonolysis and reductive cleavage. Then you can stop here. Your product will be aldehyde here, aldehyde here. Okay. It's the same starting material. If it's a fully substituted one, then product is the same. Oxygen in both sides, same. Oxidative, reductively, no difference. But if there is a chance to generate aldehyde, oxidative cleavage generate fully oxidized acid and CO2. If you want to stop here as aldehyde here and formaldehyde here, then your option is ozonolysis and reductive workup. Then you can get aldehyde here and aldehyde here. Okay, another reaction. So this one we could get from double bond into this. What reagent did you use? Dihydroxy group from alkene. 모른 척하고 그래. 동그라? Osmium tetroxide, OSO4, can add OH. And then if you wanted to cleave in the middle, you use periodate. Then it is breaking up and then generated this oxygen. Seems like this is a two-step reaction, right? One-step reaction we just have seen here, ozonolysis or the permanganate, and one-step reaction from alkene, breaking up and then adding those oxygens. Here, hydroxylation first, and then for iodate, then you can the cleave oxidatively generate this product. So this is what we have learned about alkene. Double bond. Double bond is usually more reactive than triple bond, so that's why double bond is more important chemically. That's why we give a higher priority for the number. Triple bond, similar in a sense. So by adding this one we can skip. So using this, the unsaturated structure, sp carbon, that one not super acidic, but more acidic than alkene or alkane. That's why if you use very strong base, we can deprotonate this. If you deprotonate, we can generate the carbanion. Carbanion can be nucleophile or base. And if you add now we know this kind of a material, alkyl halide, good electrophile. Then this attack here and release this bromide, and we can generate this product. This reaction, SN2 or SN1? Most likely this is SN2. This is a primary alkyl halide, right? SN2 reaction, we didn't say at the moment SN2, but we learned that kind of things. How to generate this carbanion, starting from acetylene, triple bond, and we can deprotonate using strong base, amide reagent, sodium amide. So one side can be done, then the other side also can be done. Second reaction also can happen. Deprotonate using same reagent, and then adding another alkyl halide, then we can get asymmetric one here and here. Okay. Now here, triple bond and HX. We have seen this with the double bond. Double bond and nucleophile, capturing this proton, and then X added there. Right? Similar things can happen. A little less reactive, but can be added. Once it is done, then the next step is maybe faster. Next reaction also can happen. Now the product is a Markovnikov or the anti-Markovnikov. This is Markovnikov. Okay, that condition is followed here. Similar reaction again. Now the HX X2, then first X activate this, then second X attack behind, then first step is XX. Second one, 4X. Okay. Now here oxymer equation, similar reactions, but not H plus, Hg, mercury. Then Markovnikov product we can expect. And then product is hydroxylation. Now funny thing here is the first hydroxylation can happen more substitute position. Now this has another double bond nearby. This is what we call NO. Alkene and alcohol, enol. Enol can make equilibrate to its tautomer. So enol form to ketone. So once this is formed, before it goes to the next step reaction, it is rearranged to generate this ketone. Oxymer creation gives you a Markovnikov product. Means hydroxyl group is added here, more substituted position. That's why this one, OH is added here, not here. This is the inner side, that's why the product is a ketone. Then we can compare this with hydroboration. Hydroboration is adding hydroxyl, but it's the opposite position. Right? Hydroboration, oxygen is added here, OH is added there. Because it's added here, that's why it is rearranged. It's not ketone, it's aldehyde. Oxymer creation, CO double bond happened here. Okay? Hydroboration, CO double bond is actually happening here. 이 정도가 여러분이 배웠던 단어 중에 알카인에서 가장 세련된 반응일 거야. 이 정도로 들을 수 있으면 알카인에 대해서 옥시머 큐레이션을 이해한 거고 하이드로보레이션을 이해한 거고 어느 포지션에 들어가는지 위에 레인지가 되어서 뭐가 맡겨져 있는지 정도는 가장 세련된 반응 정도입니다. 오케이, 하이드로제네이션. Similar way, if you use palladium catalyst, then reaction does not stop. It's adding one, and then after alkene, it's adding again. Sometimes we don't want to go, let them go to the end. So we want to stop in the middle. Then intentionally break that reagent by adding toxin and deactivate. So Lindler catalyst is only allows the first step reaction, and then this product can be stopped in the middle. And this product is cis or trans. Always cis because it's a syn addition. Okay, starting from alkyne, if it's added like this, it's a syn addition. That means two hydrogen was added together. If you wanted to make a trans, still there is an option. What is the option? Dissolving metal, transfer that reagent one by one. Lithium can donate up the electron one by one. That's why lithium and the plastic solvent, they can donate one by one, proton source and one electron. Add the first and then the other side. Then more stabilized trans can be formed. Okay? If I give you starting material and then end product and describe your reagent, then you should choose the right one. Okay? I think that's okay. Now alkyl halide. Recently we have learned. alkyl halide, SN2, SN1 이거 배우고 나면 유교학 절반은 배우는 거라 그랬지. 이거 배우고 있잖아. 앞에서 우리가 배웠던 반응들 그때는 모르고 지나갔지만 지금 다시 보면 SN1, SN2 이런 부분 다 설명이 되는 반응들이 있어. 2학기 때 배우는 반응들이 계란 확장들이야. 그래서 이 정도를 잘 정리하면 유교학의 기본은 한계가 다음 주까지 남는 시간 동안 이걸 잘 정리하느냐 그냥 그게 그거 같고 이게 그거 같고 할 때마다 헷갈려요. 그러면 2학기 때는 계속 헷갈리겠지. 잘하자. alkyl halide. So if it is allylic position and bromine Br2 can react here, but usually it's messy. So it's a radical reaction. So that's why small amount generating MBS and bromosuccinimide 부족하진 않은 목걸이도 좋아. MBS라는 이름 정도 알면 좋겠어. 그러면 allylic position에 cleanly one bromination can happen. And alcohol usually is not good living group, hydroxide. But if you have an acid, it's a different story. Acid is added, then protonated here, and water is a living group. Then that's relatively good living group, especially in SN1 to form carbocation. Then X can be replaced with this one. Reactivity wise, tertiary is much higher. That already implies that this is not SN2, this is SN1. Carbocation is involved. SN2, always the nucleophile should attack the electrophile at the same time. Inversion happens. And stereochemistry is very well controlled. And this reaction, typical SN2 reaction, and then SOCl2 is attacked here first, and then Cl minus coming back and behind here. In how many inversion happens here? 2, 1, 0, 0, 1, 2. 2 한 사람은 나중에 피자 2개 먹어. 아니야, 먹지 마. There's only one. 자, let's look at oxygen attack here. Chiral center is here, right? Oxygen attack here. That's outside of chiral center. The first step, no inversion. This position is the same. Chloride comes back, attack here, and then inversion happens. Only one inversion. Okay? PBr3, exactly the same. Oxygen attack here, and then Br minus is released. Reaction happened here, it's outside of chirality center, no inversion. Br minus coming back and then attack here. Now it's a change. So if this is R, then the product should be S. Okay. We have learned similar things with tosylate. Adding tosylate group, tosylate added, and no inversion. Because it's exactly the same way oxygen attacks the tosyl. When another nucleophile comes back, then one inversion happens. Okay? 그 구분 잘 해야 돼. Now usually if it is a carbon the halogen delta plus delta minus always electrophile. We can change it into nucleophile by adding metal. Metal is electron donating, so give that electron to here and to here. That's why carbocation character becomes carbanion. Change the polarity. And similar things, this reagent we call Grignard reagent. So magnesium can donate to 2 electrons, one here, one here. Similar reagent we can generate by lithium, but lithium can donate only 1 electron. That's why we need to have 2 equivalent to lithium. Lithium magnesium is a hard or soft? It's a hard. If it's a hard, then the nucleophile has a better chance to behave as a base. It is preferred to react with a proton rather than carbon. So to make it softer, the option is we add transition metal, like copper. We draw those reagents something like this. Actually, nobody knows the exact structure. It's somewhere maybe copper is added that can make that electron a little more happy covalent bonding around here. Covalent bonding means it's not very hard. It's kind of a softer the carbon. Then it can act better nucleophile. Now, so using this, and then we have a better chance to get electrophile and then attack this one SN2 type of reaction, and product can be formed. If this electrophile is a chiral, then you can expect the inversion can happen here. That's SN2 reaction. So as one coupling reaction, we have learned the Suzuki coupling. It's a little more complicated. It's not SN2 type, but one side is a moronic acid, the other side is alkyl halide, halogen catalyst. It's a little more complicated mechanism here. We've got a metallic one, so we are not going to discuss fully in detail. 이거는 아마 대학원에 가서 어드밴스 오르가닉 스코어나 어드밴스 에너지 스코어일 텐데, 그렇지만 반응 자체는 대단히 유스풀한 반응이기 때문에 아로마틱 그린 기리스로 카본 부분을 연결하시는 반응은 거의 없었어. 이 반응이 그 길을 열었기 때문에 중요한 반응이고 최소한 이 정도 조금은 쓸 수 있으면 좋겠어. Suzuki coupling. Okay, this was the alkyl halide, the first chapter. And second chapter, we have studied mainly about whether the mechanism is E1, E2, SN1, SN2. All the reactions, there is a nucleophile. And then nucleophile may attack directly here. And then this is the leading group. Then there could be either SN1 or SN2 S reactions. If the nucleophile attack not carbon, if it attacks proton, then indirectly attack here and then push and push. That's E2 reaction, similar to SN2. But SN1 and E1, it has carbocation as an intermediate. Before the reaction goes, you can form carbocation, and you can so if this halide is removed first, even before the nucleophile attack, and you generate the carbocation as an intermediate, then this reaction can be either SN1 or SN2. If nucleophile is matching together with this, then this is SN1. And reaction profile wise, this reaction this type, and this is carbocation. All the kinetics happens here. Only one component is involved in the kinetics, this one, not nucleophile. Nucleophile amount does not change the reaction speed. Only electrophile amount, that's why this is called as one determine everything. This one is not nucleophile, electrophile. Forming up here, and reaction speed is done. Next step, this one, it doesn't matter. This accretion energy is so small, so any weak nucleophile even can attack this position. That's SN1. SN2 should happen together. Nucleophile is important, electrophile is important. If you change those nucleophile double amount, reaction speed doubled. Electrophile double amount, reaction speed is also doubled. That's why we call it SN2. This two is one is electrophile, one is nucleophile, and this one if you measure those reaction speed, you have most of them is involved here. Second order reactions. And second order, but seems like the reaction profile looks like a simpler, but this one should have transient state. SM1 should have intermediate state. Okay. This is SM2, and then once this is removed, then another chance of this carbocation not reacting with the nucleophile, it can be eliminated by removing one proton. Then this reaction is E1 reaction. The E2 reaction should happen together, similar to SM2. Strong base attack here and push down and lead. Then E2 reactions. Exceptionally, sometimes there is so-called E1CB reaction. Before the X minus is removed, proton is removed first by base. Exceptional case, because this alpha position of carbonyl, this carbon anion can be stabilized by resonance. So when it has protic the acidic position on alpha position of carbonyl, it has a chance to generate the carbon anion as an intermediate. And then X minus is removed later. Product seems like B product. But here this happens only when it has carbonyl nearby. So this is kind of exceptional case. So general case wise, it's more E1 or SM1 through carbocation. SM2, when it happens usually with primary alkyl halide. If it is tertiary, forget about the SM2. Tertiary case, the best option is it can generate carbocation. Then the product will be SM1 product or E1 product. E2 product, if you prefer, you'd better to use a strong base. Magnesium reagent, lithium reagent, kind of a strong base. Then you have a better chance to shift the reaction into E2 reaction. SM1 reaction, the most important thing is the stabilization of carbocation. You utilize a polar solvent, protic polar solvent, more water. Then the reaction is preferred to go to SM1 reaction. Primary case, most likely SM2. Tertiary case, either SM1 or E1. Secondary is a mixture, all the time mixture. Now you can choose to push this reaction to which direction a little better than blend. Okay, this is what we have learned. And then this example I gave you, when the stereochemistry is changed, and PBr3, PCl3 associated to same way, this reaction is inversion. Okay, this one, as an end result, it seems like this is a retention. But in reality, actually, that's a double inversion. Internally attacked first, and then attacked by outside the nucleophile. Inversion of inversion, that's why the end result was retention. This one, I gave you as an example in the last lecture, and then again, today's lecture. Okay, this is the summary of what we have learned this semester. 자, 시간이 조금 빡빡하게 두 번째 파트를 마치기는 했지만 여전히 아직 일주일쯤 시간이 남아있어. 아무튼 목요일이니까 여기에 일주일 다른 수업도 시험 준비들 해야겠지만 유기화하게 이번 일주일 시간을 잘 보내서 활용하는 게 굉장히 남는 것입니다. 여러분들이 뭘 전공하든지 관계없이 유기2를 한 사람은 또 그렇고 이번 일주일을 잘 투자해서 잘 정리해두면 유튜브가 훨씬 쉬워집니다. 유기를 다시 안 들을 사람도 이 정도를 잘 정리해서 노트라도 손에 쥐고 있으면 필요할 때 찾아보면 평생 뒤에서 먹을 수 있습니다. Okay, so this is the last class. So 조교님들이 피자를 싸우는 것 같은데 일단